before I get started, I wanted to mention that most of the results I'm going to talk about are not just my results, but results from a large group of people who participated in Seroussi, ISMIP 6, ISMIP 7. And so I really want to emphasize that these results are from a large group. Really happy that the entire community can participate, not only ice sheet modelers, but also oceanographers, atmospheric scientists, climate scientists that help us put ice sheet in the right context within the Earth system. So when I was preparing this talk, I was looking at the seminars that you've seen in the past, and like by now you're probably all like ice sheet experts. And so I thought I would jump quickly on the introduction. And I just want to, you've all seen this figure from the last IPCC report showing the global mean sea level change relative to 1900 with projections in the future for different carbon emission scenarios. And they have their uncertainty, both low and high emission, and then these dotted low likelihood, high impact storyline that include ice sheet instability processes. And so the IPCC report concluded that the largest uncertainties in future sea level and cryosphere change are related to the Greenland and Antarctic ice sheets, and that remaining deep uncertainty relates both to ice sheet processes and the atmospheric and oceanic conditions stimulated in polar regions. So that's what I'm going to talk about today, the ice sheet part, component of sea level change. And so where did we get there for the last IPCC report? So instead of an introduction talking about why ice sheets are so important, because I think you all know that, I just want to bring you back a few years back before this IPCC report, and actually towards what was happening for the previous IPCC report. So where do we come from? So if we look at what was going on for the previous IPCC report, so IPCC Era 5 ice assessment, at the time, there were few ice sheet models that were able to do large continental scale simulations. This is one example of such similar effort from Seroussi. And so Seroussi was the main effort, international effort looking at large-scale continental projections of ice sheets. And you can see here, this figure here shows the evolution of ice sheets and their contribution to sea level in millimeters of sea level equivalent for a period going from 2000 to 2200. And there are a few things you might want to notice here. First, you have six ice sheet models that participated in this effort, because that's the only models that could take part in that at the time. And we also see that the numbers kind of all around the place. We see some models showing sea level decrease over that period. Some have increased, and the rates are very different. The shapes of all these curves are all very different. And this was for a scenario from the AR5, and so using climate forcings from yet the even previous assessment report using AR1B projections. And so these were some results under constant climate conditions. And then what was used for Seroussi and so for AR5, this was the atmospheric forcing used for Seroussi projections. And so we had for this A1B scenario results from climate models showing the mean surface temperature anomaly and the mean precipitation anomaly. And so these results were used. And then from that, we applied this condition using 1 times the A1B anomaly, 1.5 times the A1B anomaly, and 2 times. And so that's really crude, just using this one scenario and kind of trying to extrapolate for that, just multiplying atmospheric conditions. If you look at what was done for oceanic forcing and look how the role of the ocean was taken into account, it's even worse. If we look at what was applied, we had these models with constant climate conditions. And then to look at the impact of warming oceans, we really didn't have much idea of what was going on in the ocean. So we added 2 meters per year of melt under all ice shelves in Antarctica, or 20 meters per year additional melt under all these ice shelves, or 200 meters per year additional melt. So really, really crude forcing. What was the result of all that? Well, so Seroussi was the first continental scale ensemble of projections, but it has many, many limitations, and I just showed you a few of those. First, the ice models had limitations themselves. So Some of these models had no ice shelves. They were not able to simulate ice shelves, so they had only grounded ice. And so what happens when you add even crude melting under these models where there's no ice shelf? Well, you just apply the melt at the front. Another thing is that some of these models had no ability to have moving grounding lines in the models. And so we know this is a really key point to evolution of Antarctica, so another big limitations. They also had problems initializing with releasing conditions, and I'm going to talk a lot more about that today. We saw also that climate models were from the previous iteration of the climate model, the CMIP, the coupled model intercomparison project, so CMIP-4, and the ocean forcing was really, really highly idealized. What was the result of all of that? Well, the IPCC AR5 could not take these kind of projections into account. And so it was based on extrapolating observations, expert simulation, but no physical models were included. And so we went a long way from that. And so where are we now? So what I'm going to show is like some of these results that were used for the last IPCC, as well as some recent results that were published since the last IPCC report. So where did that start? So we saw that at the last IPCC report, the ice sheet models were able to do things like, as I've shown, for sea rise. There was also an effort funded by the EU, ICE2C, that kind of similar results. And moving forward, ice sheet modelers got all together and decided that, well, first it made no sense to have two different efforts. We really want to collaborate together to provide the best possible projections. And that's how ISMIP-6 was born. ISMIP-6 is the ice sheet model intercomparison for CMIP-6. And so for the first time, ISMIP-6 has been part of the CMIP. So you see here on the right, it lives in the ocean land ice part. And its goal is to estimate future sea level contributions for from the Greenland and Antarctic ice sheets and the associated uncertainties. And so that's kind of how ISMIP-6 started. What happened during its lifetime all the way to the IPCC AR5 report? The first thing is that, as we've seen, ice models had lots of limitations. And so we really focused on giving modelers the opportunity to improve the models, think about initial conditions. And so, again, I'm going to talk just about Antarctica today. Lots of these efforts, they are similar efforts for the Greenland ice sheet, but that's for another day. So what was the idea with ISMIP Antarctica? The idea was to focus on initial conditions and initializing models. The approach was that modelers, this is a community effort, a volunteer effort. There's really unfortunately, no dedicated funding for these things. So people are really interested. We have a wonderful community, but we can't really have strong constraints. So the idea is that models come as they are. However, we've had noticed from sea rise that there are a few things that really are key if you want to simulate the Antarctic ice sheet, and that's not going to come as a surprise. First, you need to model to include ice shelves. Otherwise, and you're missing a big part of the story. And also, these ice shelves, we know that grounding line moves on all kind of timescales, but you want to be able to capture these changes. And so models need to include grounding line evolution, advance, and retreat. Mostly retreat if your climate is warming. And so that's how ISMIP worked. We see here on the left, the initial ice shelf extent for the models. And we had about, I think it was for ISMIP, I think it was like 15 or so ice sheet models that participated. And we see that if we look at the ice shelf extent of these models, then we see that they all capture here. So on the left, you have here the number of models that stimulate any point as an ice shelf. And so we see these dark blues shows that where all the models show that these places are ice shelves. So we can capture the large ice shelves, but we see also that the extent both of the ice front and the grounding line can vary significantly from one model to the next. We can, as the idea here is to see how the models are able to capture initial conditions that represent today's condition that we have observed in Antarctica. We can also look at how well they can capture the ice thickness or the ice velocity. And so here on the right, we have the root mean square error in ice shelf, in thickness for the entire ice sheet, as well as the same thing, root mean square error for the velocity of the entire Antarctic ice sheet for these different models. And so you see there's a variety of ability to capture these conditions. That depends on how the models are initialized, if they're initialized today with present-day conditions using data assimilation, or if they are run over long periods using paleoclimate spin-up or steady-state conditions, in which case they tend to be further from present-day conditions. So that's kind of like how models can capture today's conditions. And then we want to see how they are going to evolve in the future, because it's not just about capturing today's conditions, it's also about being able to project changes. And so the first experiment here on the left shows what happens if you apply constant climate conditions similar to today over the next 100 years. So you see that under present-day conditions, some of these models show a large mass gain, 100 millimeters of sea level equivalent, up to more than 200 millimeters of sea level equivalent for some of them, while some other models show a mass loss up to almost 200 millimeters of sea level equivalent. So there's really a large uncertainty in the trend that these models have under simple constant climate conditions. The next thing we are interested in is looking at how they respond to changes in climate conditions. And so to really understand what was going on, we separated changes into changes in surface mass balance and changes in ocean conditions. So the middle plot here shows the impact of changing surface mass balance anomaly. So in that case, we doubled the surface mass balance. We wanted something relatively easy to look at the response. And there's a star here because this is the difference between this experiment with double surface mass balance minus changes from these constant climate conditions. What do we see here? We see that the response to these changes in surface mass balance are the same for all the models, like some a little variability that was due to the initial extent of the ice sheets, but pretty much the response is the same for all of them. If, on the other hand, we look at the impact of changes in ocean conditions, and again, we wanted something simple here, so we doubled the melt that we are observed today that's estimated from remote sensing observations. And so if we double this melt, we see that the response is kind of all over the place. We have some models like the ones here in the middle. I hope you can see my mouse. That have almost no response, very little change in the increase in ocean melt, while other models has a really drastic response, like 10, 20 times more in some cases. And so in that case, we have really varying results. So that was a starting point. The next thing to try to improve ice models, where they are and what are their similarities and differences. The next thing we want to think about is that ice sheets don't live isolated from the rest of the climate system. And so they live within the Earth system. And so how can we best include climate forcings for the, in that case, Antarctic ice sheet? What I showed earlier was very crude. And so we want to instead use results from global climate models. And so that's when the entire community of Earth scientists, including many, many disciplines, got involved. And we came up with this protocol on the right. Seems a little complicated from far away, but I'm going to break this down into a few pieces. So the first thing is that we want to use forcings from climate models, and so we have to select them. How do you select them? Well, same as ice sheet models, climate models have different strengths and weaknesses, so we want to use climate models that capture polar conditions relatively well. And so we looked at atmospheric temperatures above the Antarctic ice sheet, ocean conditions in the Southern Ocean, and from that, we kind of ranked the models according to their ability to capture conditions today. And then when we want to look at future scenarios, as I've said, one of the goals of ISMIP7 is to look at, as ISMIP6 was to look at the uncertainty in projections. And so we don't want to select climate models that all tend to warm a lot more than the other ones or a lot less. So we want to really capture a range of conditions with some climate models having more or less warming. And so that's how we selected climate models. The next thing is that how do we use these climate models? We want to have forcing conditions at the ice surface. So we need atmospheric forcing. And for that, we just used the result from the climate model. So applied surface temperature and surface mass balance anomalies compared to present day conditions to account for biases that can happen in these models. The next thing is oceanic forcing, and that's a lot harder because two things. First of all, ocean conditions tell us what the ocean temperature and salinity are, and so there's quite a work to do to go from ocean conditions to melt applied under Antarctic ice shelves, and this is a whole different topic. So I'm sure people have talked about that, but basically we need melt parametrizations. And the other thing is also that these climate models don't simulate ice shelf cavities, so we have to extrapolate conditions from outside of ice shelf cavities on the continental shelves and bring them into the ice shelf cavities. But let's assume we can do that. What are the results? So here are the main results from ISMIP6 showing experiments performed for the Antarctic ice sheet. You see we mostly focused on high emission scenarios. And then we have on the right the ice sheet models that participated. And you see here a large diversity of models. We can look at the stress balance they include, the numerics, finite element, finite differences, the resolution of these models, how they are initialized, the melt parametrization I just talked about, ice calving front. And it's in 15 seconds, I'm obviously not expecting you to remember all of that, but the idea here is that we really capture the range of diversity parametrizations that is part of the ice sheet community today. So if we do that, here are some main results. We see under 6 different, so using forcing from 6 different climate models, all using high emission scenarios, the evolution of the ice and in terms of sea level equivalent in millimeters per of sea level equivalent for all the ice models I just talked about. And so the thin lines show individual simulations for one ice model and one climate model. And then the thick lines show the average for each of the climate models. And so we see here that there is a range of uncertainty, both when we use the same climate model. So for example, if we take HGM2, we see that this tends to have the largest sea level contribution from 26 centimeters from almost 0 to 26 centimeters of sea level rise, depending on which ice model you take. But you can also see that there are differences depending on which climate model you take. And so, for example, all the results with IPSL tend to have mass gain, while all the results from HGM had mass loss. So what's going on here? We also see that we have most of the results are kind of closer around 0. So what does it mean? Like nothing's happening? So if we dig a little further into these results, we can see actually that there are a lot of things going on. And we have like competing regions and competing processes. So here, these are exactly the same results, showing, focusing just on the average change and the uncertainty around those. So like these bar graphs show this contribution to sea level rise for the West Antarctic ice sheet, East Antarctic ice sheet, and the peninsula. And so that these are the mean results, as well as the bars showing the range of results, standard deviation. And so on top of that, we can look also at these diamond plots that show the surface mass balance contribution. And these results are all subtracting the control experiment with constant climate conditions. So we see that in West Antarctica, there's not much change in surface mass balance, and there is a contribution to sea level. So what's happening? There's limited changes in surface mass balance. Oceans gets warmer, and so there is, even though melting ice shelf does not contribute directly to sea level rise, there is acceleration of the feeding ice streams that discharge more ice, dynamic processes, and we end up with some mass loss. If you look at East Antarctica, the results are quite different. There's quite a negative surface mass balance. What does that mean? That means with these warmer conditions, there is more moisture trapped in the atmosphere, more surface mass balance, more precipitation. And so the East Antarctica is gaining more precipitation. But you also have the ocean playing a role. And so if ocean gets warmer, you also have a dynamic response to that, dynamic thinning, acceleration. And so the difference between this change in surface mass balance and the total is the dynamic contribution from the ocean. We see here, and so we see what's the picture here. Not so much is happening in the peninsula, so let's not talk much about that. West Antarctica, we had little changes in surface mass balance and a lot of dynamic changes. East Antarctica, we have a lot more surface mass balance, more precipitation, and some dynamic response, but not enough to offset the the mass gain. And so we have these competing processes from warmer oceans, warmer atmospheric conditions, and also competing regions with West Antarctica and East Antarctica having a different response. So, okay, so that was a summary of these ISMIP6 results. As I said, that was one of the sources of information that was used for the last IPCC report. And so what did we learn from that? Well, first we saw that we have a much larger number of ice flow models that could take part compared to the previous efforts. Ice flow models still have some limitations with the representation of ice shelf extent. Now they can all do it, but the extent can vary from one model to the next. Grounding line evolution is included, but initial conditions can have some limitations and not always be able to capture conditions. Climate models were coming from both CMIP5 and CMIP6 because there was delay in CMIP6 results. And one main thing is that we really have improved things a lot in terms of capturing climate conditions. And so both mostly oceanic forcing as well as atmospheric forcing is a lot more realistic than it used to be. Okay, so that was what was done for the IPCC. And then that was all about 2100, but the world is not going to end in 2100. And we saw that there were large changes, but not that big. And so what happens beyond 2100, what are the regions that, if we continue looking at future results, what's going on? So we continued using the same protocol that I just described. We looked at evolution of ice sheets for Antarctica until 2300. And so most of the previous efforts have used conditions from the end of the 21st century, so typically 2080 to 2100, repeated over the future, when in this case, we really wanted to rely on conditions that were simulated by climate models until 2100. And so again, I'm going to continue focusing on high emission scenarios. Again, here we have a list of all the models that are participated. So you see the list keeps growing and growing. Again, lots of information, but same thing. You want to look at models using different stress balance approximations, different resolution, different ice front calving mechanisms, melt parametrization, and so on. So here we have 16 models, modeling groups using the 11 different ice flow models. And we have, from them, we had 40 sets of simulations. What does it mean? That means that some of these groups, as you can see maybe here at the bottom for VUW, Wellington in New Zealand, submitting 11 sets of simulations with some varying parameters for melt, resolution, and things like that. So a total, we had 390 simulations. Easy to say that was a little overwhelming, but we could still draw some interesting conclusions from these results. So this is what we had looked at so far, 2100, and we saw that we had some tens of centimeters of mass gain or loss. If you start looking at what happens until 2300, you see that the results are drastically different. And really, 2100 is kind of the turning point where things start to really accelerate and change very rapidly. Same as what we've seen before, we have here 4 different climate models. And so each line here shows a combination of one ice model with one climate model forcing. And on the right, we see the range of results for each of these climate models. So the simulations run with CCSM4 tend to have the least change in ice volume and the least contribution to sea level, while the other 3 tend to have like relatively similar results with up to 4.5 meters of sea level change by 2300. We can also look at this the other way around. So for each ice model, so you see here, so this is just for 2300, you see here at the bottom for the different ice flow models, the spread of results for all these 4 climate models. And so we see that some of the models, let's take the first one, that's my model, there's a relatively small range of results when you use forcing with these 4 climate models, while for other models, let's take the last one, the black one on the right, we see that there's a really much wider range of results when we use all these 4 climate models. So there's a spread of results in both what climate model you're using and what ice flow model you're using. What's happening in by 2300? So I thought it should be a good time to add a movie here. So just wake up people. This is one of these models, kind of an average one, not responding too much. And we see the evolution of the Antarctic ice sheet until 2300. And so that was too fast. Maybe I'll just let you watch and then I'll talk over that again. So go starting in 2015 and going all the way to 2300. And so maybe let's start this again. I hope we can do that. So we see here at the beginning, typical ice Antarctica today. By 2300, we see that some grounding lines here filling the Ross ice shelf start retreating. Same with Ronnie Filchner. And then just after 2100, things start to change a lot. Ross ice shelf disappears, Ronnie ice shelf disappears. And then we see towards the very end that Thwaites Glacier has a large retreat also happening. So by 2300, most of these large ice shelves, say including the Emery ice shelf, are pretty much gone with warmer ocean conditions. So that was just one particular example, now we can look at all the results from all these ice flow models. And so here showing for 21, 22, and 2300, the change in ice thickness compared to the beginning of the experiment in 2015. So we have on the top row, the mean thickness change, and on the bottom row, the standard deviation. So 2100, that's what we've seen before. The ice shelves are melting and thinning. In some places, there's some inland propagation of the thinning, not that much. By 2200, the picture has to be quite different, with extensive thinning upstream of many of the Ronnie Filchner ice shelf and the Ross ice shelf, as well as above Thwaites Glacier. And then by 2300, these very large thinning has extending to most of the West Antarctic ice sheet. And if we look at the standard deviation, that's really interesting because the standard deviation is like almost zero on the Ross and Ronnie ice shelf, because all these models simulate that these ice shelves are pretty much gone by then. And then same for areas just upstream of these grounding lines, but then a lot more uncertainty and differences between the models when you look at the Amundsen Sea region. If we continue looking at that, another thing that we want to look at is the grounding line retreat. It's really a good indication of like how things are going. And so here, these figures shows for the same timeline, and at the top is for all of Antarctica, the bottom is just the same, but focusing on the West Antarctica, since that's where most of things are happening. The percentage of the ensemble that shows ungrounding at a certain point. And so how many of these models have simulate a grounding line retreat? And so we see that by 2100, there is some retreat, mostly Cyprus coast, also Bergenstock ice rise here. And then by 2200, things start to really accelerate. And by 2300, we see that in some regions, there's a really strong agreement, like it's dark red. So most of the models, if not all of them, have retreats on Cyprus coast, Bergenstock ice rise. While in other regions, these blue colors show a lot more disagreement, with some of the models showing retreat on most of the West Antarctica, a complete collapse, but a really strong disagreement of where the grounding line will be there. These large retreats are really interesting, and so we're going to focus on that for just a few more minutes. And so now we're going to look at these. So you see here on the left, these three lines going on Thwaites Glacier, the Cyprus coast, and Bergenstock ice rise. And we're going to look at the grounding line retreat in these regions. And so I'll walk you through this figure step by step, because usually we don't look at it this way. So here we're looking at this line on Thwaites Glacier. And so we have here the current grounding line is on the left, and then we have the distance from this grounding line, and here is shown the topography of the bed. So we see the bed is mostly sloping downward inland, and these arrows show the uncertainty in the bed topography. And then we can look at how the grounding line is retreating in our simulations. So here on the vertical y-axis, we're going to have the time from the beginning of the simulation at the bottom, 2015, all the way to 2300. And so if you have a vertical line like this, that shows that the grounding line is in the same position all the time, so nothing is retreating. If on the other hand, you have like a horizontal line, it shows like an infinitely fast retreat where the grounding line just has a runaway behavior. So if we take, for example, one of these models, we see that grounding line starts here. That's the position for at every year. We see that it's very stable, starts retreating, then gets anchored on that pinning point here, and then retreats more towards the end. So that's for one of the ice model, and then we can add all the other models. What do we see here? First, we see that the initial position varies between the models. That's something we talked about already. And we see that like about half of the models have their grounding line position that stays within the initial maybe 60 kilometers from the present day grounding line. In this first half here. And then we have the other half of the model that has a large retreat going 300-400 kilometers from the present day grounding line position. And something that's really interesting is that the retreat, so the slope shows the rate of retreat. And so we see that the rate of retreat is really similar for all these models. And so the timing at which this large retreat starts varies between the models. But then once it's engaged, the retreat is mostly dictated by the geometry of the glacier, and so they all retreat at the same time. That's something that a number of studies had looked at, but we had never been able to do that with a large ensemble of models, and so this is really confirming the critical role of bed topography and ice geometry for these large changes. We can do the same on these other two glaciers, Buggenstock Ice Rise and Saipol Coast, showing the retreat. Buggenstock has large retreat. All the models retreat. That's what we had seen before. Like all the models agree the grounding line is going to retreat really far. The exact rate of retreat is a little less similar than for Thwaites, but they all agree. And then all models gets the grounding line stops on this prograde bed slope around here. Saipol Coast, same thing. We have a relatively good agreement in terms of the rate of retreat, and most models show a large retreat for hundreds of kilometers. Another thing we can look at is the role of ice shelf collapse. And so all these experiments I talked about so far had ice shelves mostly thinning and at some point becoming so thin that they would stop existing. But we know that ice shelf collapse, we've observed that in the peninsula. And so now we look at using very simple conditions, simulating ice shelf collapse. And so using, again, these 4 climate models, we can see the timing of ice shelf collapse as estimated by the climate models. And we see that, well, ice shelf collapse has already started in the Antarctic Peninsula. And then it's going to propagate towards the coast. And here we have 2 climate models from CMIP5, so CSSM4 and HGM2, and they have a very different response. CCSM4 has large ice shelf collapse because there's a lot more liquid water at the surface of the ice shelf, while HGM simulates almost very limited ice shelf collapse. If then we look at the 2 models from CMIP6, CSM2 and UKESM, we see that they have a much closer a way of simulating ice shelf collapse with large melt happening at the break-in slope where you have these Carpatic winds that play really important roles. And actually we were able to simulate the largest iceberg that was you ever dreamed of. But so what happens when we do that? This is the impact of including ice shelf collapse in our simulations. And this is really just imposing ice shelf collapse based on that timeline. And then modelers are able to use that in the way they want, what they think makes most sense for their models. And so we see that adding ice shelf collapse on average adds another 1.1 meters of sea level equivalent by the end of 2300 when ice shelf collapse is added. And in that case, you have more retreats. So same figure as before, the percentage of models that unground for 21, 22, and 2300. And on the bottom row, you have the percentage difference of models that have their grounding line retreat compared to the previous cases when we add ice shelf collapse. So about 20 to 30% more grounding line retreat in large sectors of West Antarctica. Okay, I think another thing that we want to think about, and I know you have several seminars, including very recent ones, talking about bedrock adjustment, glacial static adjustment, and so I thought I could just say a few words about that. What happens with these models? Bedrock adjustment, when we look at 3 centuries, starts to be really important, and so 2 things are important here. Sea level, what I showed was just ice volume above flotation, but sea level is more than just ice volume above flotation. And so we need to correct for density difference between fresh and salty water. That's about 3%. And then recently there's been 2 methods proposed by Adhikari et al. 2020 and Golser et al. 2020 showing how the bedrock, the changes caused by bedrock adjustment due to the solid earth response in ice loading should happen. And so when this jury is still out in terms of like how to best include that. And so we see the results here with and without this correction, and we see that there are small differences, about 10%. If we look at a table, might be easier, showing the difference between the volume above flotation that was calculated and that I've been talking about before, and this improved method to include sea level bedrock adjustment, we see that there's about 5 to 10% difference. And you see here what the models did for the bedrock adjustment. First, most of the models do not include any of that, and then the other models have either viscoelastic response or an elastic lithosphere, a relaxed asthenosphere, that's a mouthful. ELRA, I should say it this way, bedrock model. And so another thing you can see here is that a few models, you might have seen that, and that's why I wanted to mention it. A few of these models seem to have more than 10% difference compared to the previous calculation, up to 20, 30%. These are models that have actually a really small response to changes, and so adding a little more, the correction is not that big, but it represents a non-negligible fraction of the percentage. But what is more important here is these models that include bedrock adjustment, and we see that in that case, the two methods differ, while they were not very different in the previous case. For example, 11 and 17%, or 28 and 57%. And so there's a really large adjustment when you include that, and depending how you compute the sea level. So I know you have seen several seminars on that, including recently. So I'll stop there. Okay, so we've seen a large number of curves showing various response of the Antarctic ice sheet in future projections. I wanted to talk a little bit also about why these differences. What are the sources of uncertainty in these projections, and what can we learn from that? So first, we're going to go back to the 2100 results, the main ISMIC results. And here we want to look at the sources of uncertainty and there are two main sources. The first one is which ice model you use, and the second one is which climate model you use. And here again, I'm just focusing on high emission scenarios because that's where we have the most data. Another thing is, like, not every ice model was able to simulate to do every experiment. And so first we need to use emulation to simulate experiments for which we don't have results. And so another source of uncertainty is the simulation. So what if we look at that? So this figure here shows the percentage of the uncertainty coming from the climate model used, the ice model used, ice and climate interaction, which is mostly ocean, everything linked to ice-ocean interaction, as well as the emulation. And so we see here that the role of the climate forcing, first, there's nothing. It's all dominated by the ice model. And as time goes, the role of the climate forcing increases to reach about 13% by 2100. The emulation, the uncertainty coming from an emulation counts for about 10% of the total uncertainty. And then the rest comes from the ice models, about 2/3, and 1/3 from the ice model that you are using. This is for all of Antarctica. But something really interesting is that we see, depending on which glacier you look at, the repartition of uncertainty can be quite different. For example, if we look at, Thwaites Glacier here, for Thwaites Glacier, the role of climate model is really small, less than 5%. Emulation is still about 10%, but then the majority is from which ice model you start with. And that's because Thwaites is already changing, and it's really hard to capture this change. And so ice models struggle with that, and therefore start with quite a different behavior. And then as time goes, the role of ice and climate interaction, so ocean and ocean feedback, becomes more and more important to reach about half of the uncertainty. If you look at Institute Glacier, the story is quite different, with the role of climate increasing drastically over time to reach about 1/3, and 1/3 for the ice model, 1/3 for ice climate interaction. If we look at Toten Glacier, the story is about the same, with like maybe equal uncertainty from these three sources. And then a really interesting case is Mackay ice stream. And in that case, we see that the role of the choice of climate model increases rapidly over time, and the uncertainty caused by the choice of climate models represents half of the uncertainty by 2100. Why is that? Well, for some of the climate model we use, let's take a step back. Ross Ice Shelf today is a cold cavity. But by 2100, some of these climate models simulate warm water intruding into these cavities. And some continue to think it's going to remain a cold cavity. And so depending if it becomes a warm cavity or it remains a cold ice shelf cavity, then the response is drastically different. And so that's why we have such an impact of the climate model. We can look at that looking at that for a few more glaciers, using the 11 glaciers that have the largest contribution to sea level by 2100. And so these 11 glaciers are mostly in West Antarctica, unsurprisingly, as well as Totten, Moscow, and Leopold and Astrid Coast. And this figure here on the left, if I can add it, yes, shows the total uncertainty in the dynamic contribution to sea level and its repartition between the same four sources that we just talked about. Again, a lot of information, but one thing that stands out is that the most of the uncertainty comes from Thwaites Glacier. And this, I know many people have talked about that, but that continues to be the same. We can do the same with the results for Antarctica 2300. And so again, doing multivariance analysis. And this time, because by 2300, the ice shelf collapse is really important, we take simulations with and without ice shelf collapse, and similarly use the uncertainty from the ensemble, looking at ice models, climate models, and ice presence or absence of ice shelf collapse. This is how the uncertainty evolves over time. Again, we saw that by 2100, the sea level contribution was relatively limited, and the uncertainty is also relatively limited, or at least limited compared to what happens by 2300, where the uncertainty is like more than 1.5 meters. This variance. And then we can look at the source of uncertainty. The choice of ice model dominates, followed about equally by the climate and the collapse and the ice collapse interactions. And so same thing, looking at the percentage of the variance coming from these different sources, we see again, starting from the bottom, we have the climate model. So we saw that the role of choice of climate model was increasing until 2100 to reach about 15%, same as before. But then after that, it remains about the same, and so it remains around 50%. Most of the uncertainty comes from the ice model initially, and then that portion decreases a little bit because other sources start to be important, including the collapse in yellow and the ice climate and ice collapse interactions. And so ice model, but still, when you look at 2300, the choice of ice model still represents more than half of your uncertainty in these projections. Okay, so I thought I should add just a few slides to conclude here. So with all these results, where are we going? Today we're thinking about ISMIC 7 and, I'm sorry?
I think your slides might have frozen. We're like stuck on slide 29. I'm not sure.
Oh, 29, that was a while ago. I was going back to 29. And do you not see that?
It's still stuck. So
okay, I can try.
You can unshare and then.
Yeah, I'll stop sharing and I'll share again. Hopefully that will resolve that. Sorry, I look now, I see there's a message in the chat. Unfortunately, I had not seen that. Okay, let's try this again. Do you see I guess I'm back to the first one. That's what you're seeing? Okay. And now Ethan can make this full screen. How is it?
Yes, we see slide 30 now.
Okay, so that's what I just talked about, the increase until 20. Okay, that will make a lot more sense. Like, where's 2300? So 2300, we see, as I was saying, the increase in uncertainty and the variance, mostly dominated by the ice models. And then what I was talking about is that the role of choice of climate models had increased until 2100, but then climate forcing, uncertainty coming from climate forcing stabilizes around 15% and remains so until 2300. Initially, things are completely dominated by the choice of ice model, and that remains the case with more of half of the uncertainty coming from the choice of ice model, even by 2300. So if we were hoping that maybe after a while, the choice of ice models and these limitations don't matter, well, unfortunately, it matters for a really long time. And then collapse also is interesting. So you can watch this is recorded, so you can go watch back the video with the actual explanation, so I don't have to repeat myself too much. Okay, so where do we go from there? We're starting to think about ISMIP 7, and the role here is key objective remains the same: to improve projections of sea level rise contribution from the Greenland and Antarctic ice sheets and our understanding of the cryosphere. And we also want to continue looking at uncertainty in sea level projections caused by model initialization, processes, climate scenarios, and so on. What are the main things we want to, and these are like kind of my personal ideas, what I think is important. So you are totally free to disagree with me. But I think as I think about where we're moving now, what are some of the key things we want to improve moving forward? The first thing is in improving our ability to capture recent changes and having improved historical projections. So if we look at, so there was a great paper by Andy Ashvanden in 2021 showing, and this is just for the Greenland ice sheet, so I guess I had to say the name Greenland to pretend I am talking about both poles. But so here we have in blue the mass loss estimated by IMBY with a consensus of several different observations, as well as in light blue, the uncertainty around this estimated mass loss from the Greenland ice sheet. And then in gray, we have all these ice flow models, and you have the same ones on the right from Heiko Galter's paper of ISMIP 6, so showing the spread of results from 2000 to 2015, showing that they are pretty much all underestimating the mass loss from the Greenland ice sheet. So what does it mean when we think about projections? If all our models underestimate the changes over the past couple of decades, probably going to underestimate projections in the future. So how can we move forward? Several things. We need to have access to accurate forcing from the atmosphere and ocean. We also have a lot more observations now. The first map of Antarctic ice flow was in 2011. I was still finishing my PhD. That says a lot. Now we have observations almost like of showing velocity almost every other week. And so how can we take advantage of that? How can we use these new observations to improve our models? Some people start thinking about Bayesian calibration, running large ensembles, or data assimilation over time. So these are all ideas to improve these historical simulations. And it's, again, including ice models, but also people who will have a better idea of ocean conditions, atmospheric conditions, melt parametrizations, and so on. So we have here this contemporary period for which we have good observations, reanalysis forcing maybe. But then if we go back further in the past or in the future, what we rely on are climate models that we know have bias. So how do we do that? How do we correct them or not? How do we transition from the deep past towards the contemporary period and towards projections? What's the best way to do that? As I said, I'm just raising questions here, not providing really answers, but like showing a few things that I think we need to improve. Another thing is that every other day we have some paper showing like a new process that's been observed by remote sensing or some new theory. These are just two that I picked because they were published recently. The first one is from Bradley and Hewitt, looking at the role of subglacial water and the grounding zone. And this has been going around for quite some time, but they looked at some positive feedback mechanisms that can cause large changes. But they also can create runaway mechanisms with really a lot of melting over large regions in the grounding zone and upstream, and runaway mechanism that can create really rapid grounding line retreats. But as they mentioned in the paper, there also are negative feedbacks that they did not include. So if we want to include that, how do we do it? Same thing with the marine ice cliff instability. It's been around for about a decade now. It's really changed our perspective on ice sheets, and showing that some retreats could happen a lot faster than what we've been thinking about. And then there was a paper published over the summer by Mordigam et al. Showing that, well, depending how you include it, the marine ice cliff instability might not have favorable conditions to appear for over a long period, because as soon as you have cliffs that develop and some collapse starts, then you also have the viscous deformation of ice, and that ice starts flowing a lot faster, and that's with this viscous flow, it starts thinning, and therefore these conditions could be short-lived. Why am I bringing these examples? Not to say they're right or wrong or anything, but to show like how science improves and advances with discoveries and just adjustments. And as we understand more, we have more observations, we refine these processes. So how do we do that when we think about projections? And we cannot give different numbers every other day. People, stakeholders, policymakers need that. So again, some questions. How do we include these latest results and still synthesize, summarize results to include that? Finally, last point, I promise, we have a growing number of simulations. And so here, going back to these 4 efforts I was talking about, Seroussi, and then INITMIP, ISMIP 62100, and ISMIP 62300, we see here the number of models that participated. And so there was mostly a large increase between Seroussi and INITMIP, and then the numbers have kind of stayed the same. And then the red line shows the number of simulations submitted. And you see that the number is exploding with like almost 500 simulations submitted for the latest results. Why is that? Well, some of these groups submitted not one set of simulations, but for Norway, for example, 11 sets of simulations with different forcing, with different resolutions, with different conditions. And so what do we do that? While other models still have one set of simulations. And why is that? Well, some models are relatively fast to compute. They have like simplified physics. So it's kind of like these Duplo things that your little kid can play with. They're super easy to put together, and you can have a bunch of those. And other models try to design with different things in mind and try to include processes in as much detail as possible, maybe run higher order full Stokes stress balance approximation and so on and so on. And so they have more complete physics, but they're really slow to run, and so can do only a few experiments. So how do you combine them? Again, I don't have much answers. Maybe emulation, data science can teach us a lot here. So I'm going to conclude here. So I'm going to conclude here talking about like how ISMIP 6 was a great success, and now there's really high expectations for us moving forward. Opportunities also to learn from other efforts. And we have many challenges that remain, thinking about how to continue improving these models, providing actionable results that are really useful for stakeholders. Also, something I did not talk about is that coupling ice sheet models with Earth system models and ensuring the long-term viability of our projects and future results. So I'll stop here. And again, thanks for the invitation and thanks for all the people who participate in all these efforts.
Okay, thanks so much, Helen. Do we have any questions? Yes, Jeff.
Hi there. Thanks for the talk. The idea of having couple climate models with ice sheets in it, of course, means that there's a feedback between the ice sheet and cavities and the ocean in terms of barotropic stream function and things like that, and which you don't get with the standalone ice sheets, forced ice sheets. So, do you think these are important processes to consider?
Yeah, great question. So when we have these models, they're based on forcing from climate model, and so we have ocean conditions in ice shelf cavities. And as I said in the previous CMIP 6, no models really were modeling ice shelf cavities. So it was mostly extrapolating condition. So it's even worse than that in the sense that it's like extrapolating conditions that are on the continental shelf into the ice shelf cavities, even if we know it's not so accurate. There is a little bit of no feedback, like the conditions change mostly with like warm waters at depth and lighter, colder water above in the water column thickness. And so that's included because when ice shelf thins, they are bathing in different water conditions. So that's the only process that's included. And so as you have more freshwater discharge, it can change your circulation, it can change things like that, which I think it is an important process to include. With so much more freshwater discharge from the Antarctic ice sheet, when we see these numbers like 4 meter equivalent by the end, that's quite a ton of fresh water that you're just dumping in the Southern Ocean. So that's, I think, is going to have a strong impact. Some climate models start to have be able to do coupling between the ice and the oceans, but then they are far and few and can only do so many experiments. So we are the beginning of that, and I think I think we're going to see a lot of progress on that field in the next decade or so.
Thanks.
For some reason, I can't put my hand up, but can I ask a question kind of following on from Jeff's comment?
Sure, absolutely, Gavin.
Hi. Yeah, great talk. And not just the talk. I mean, like, but kind of steering this process through and getting everybody to work together on a common set of anythings is a truly heroic effort. So you know, our hat is tipped to you, Sheppel, as they say. Your point about how difficult, how necessary it is to have the ice sheets coupled to the oceans and the climate, and yet how difficult that still is, resonates a lot with us. And so we've been, I mean, as you know, we've been trying to find ways in which we can do something that's better than nothing, but not quite as complicated as doing it properly. And so I'd appreciate, you know, your intuition or your thoughts on how one might want to do some kind of asynchronous coupling, or kind of do a couple of iterations to try and kind of get the zeroth order effects of the coupling, and how one might do that from your point of view.
Yeah, great. I really like how you're phrasing that in terms of like people have been trying to couple and have a fully coupled system for a while. I had a paper like 2017 looking at Thwaites, Amundsen coupling, and since then these things are really hard and take a while. So while I think we should have efforts focusing on that, because if we start today, we'll be ready in 5 or 10 years. So I think we should not completely leave that on the side. But I agree with you that meanwhile, we could have offline coupling or forcing. And so one way to do that could be that first step is that's what we have now with ice models forced by climate conditions. And then as we have these results, we can look at the impact on climate conditions. And so rerunning the same climate conditions, but with the appropriate amount of freshwater discharge from the calving, from the melting, from all of that. And so that's going to change the freshwater discharge in the Southern Ocean. We could do the same for Greenland. And with that, see how the climate models are responding to that, and how different the future projections from the climate models are with these new results. And so we have, and there's like too many simulations almost. So pick your favorite, the most extreme or the one you trust most. I think it probably doesn't matter, except that probably large changes are most interesting at this stage. And then when we rerun these climate models, how different are they? And if they're significantly different, can we do the second step and go back to the ice model and reapply that forcing to look at how different the response is? And so that would be one way to do it, whether it makes sense to do it the entire period or in chunks of whatever years. Then you can go back and forth. And the first back and forth is probably the one that's going to have the most impact. And after that, it's just refining. But at least first order would be to rerun climate models with these kind of projections. And then if there's a significant impact, rerunning ice models with the new forcing.
Yeah. So, yeah, I agree. And, you know, and there's some intriguing things in the observations, right? So I'm sure you're aware, like the grounded mass balance has increased in Antarctica.
Which that's considered. I mean, as I was showing, there's a projected increase in precipitation from climate models. So whether we believe it or not, that's what these models says. And as we were saying, and now we're starting to seeing that. So maybe it's not. Yeah, that's what it is. but it's kind of consistent. And sorry, I interrupted you. There was another thing I wanted to mention. Also, like the devil is always in the details. And so when we have this new fresh water, where do we put it? Typically, fresh water is put at the surface of the ocean, but we know its distribution through depth because we know where it's happening. We know the elevation of the ice shelf base. We know for which ice shelf, so we can have like a 3D distribution. Does that matter for climate models? I don't know. Do they have the ability to have that much precision to put the fresh water where we think it's happening? That would also be things to probably investigate.
So we think that it does matter, and so coming off that workshop that we had in February, it's been a little bit of a while coming, but we're almost done now. We've gathered both iceberg distributions from each of the ice basins for both Antarctica and Greenland. And so we have a distribution of that, and we've gone back and forth with the people that were looking specifically at iceberg melt, and it's probably too complicated to do anything else other than have a kind of a uniform distribution, kind of from like 0 to 200 meters or something, in the areas where the icebergs are melting. But that paper is. As soon as everything else gets off my desk, that's the first thing, which means it's the fifth thing that I'm working on. But we are trying to provide some guidance there to different modeling groups, and I think that there will be, people will be able to pick and choose what they feel like they want to implement. Some people will not implement like the region by region. Some people will. Some people won't. Won't do the distribution in depth. Some people will, and so we'll be able to get, I think, some sense of the structural uncertainty associated with that. And then there's of course the Sophia project, where they're trying to do controlled freshwater additions in various ways, none of which are like super realistic, but that still might get you a sense of how sensitive different models are to different formulations of this. So there is some work that really still needs to be done there, but I think we're making some progress. So you can. I'll be happy to send you that draft when it's a little bit more ready.
Sure. Yeah, that'd be great. Thanks. And I like a pragmatic approach when you have these large efforts from the community, same as what we had with ISMIP 6, now ISMIP 7. You want to have reasonably easy to implement conditions, otherwise nobody can do it. But then individual people can pick it up and bring it to the next level to look at more detailed processes.
I think that's exactly right. You have to give people something that they think is trivial to start with, and then kind of entice them to be a little bit more complicated later on. But if you give them like the whole big thing right at the beginning, then it's too much of an activation energy and people don't do it.
Yeah, overwhelming. So you always have to be pragmatic.
We agree. Yay.
Looks like Frank has been waiting for a while. Sorry, Frank.
Thank you, Hélène. Very nice talk. Very nice talk. Thanks a lot for that. You're probably familiar with the work of Jo Coulon and Anne-Christine Klose. And so they used two models, but they looked at a parameter uncertainty and a very large parameter uncertainty. And the result of that is that then the climate model uncertainty becomes more important than the ice dynamics uncertainty. So what would happen here, and how would you ideally deal with that if we include parameter uncertainty also in ISMIP 7 or in any other future in ISMIP intercomparison, because that could change. I mean, it's also in terms of weights that it becomes quite complicated. What is your opinion on this?
That's a hard one. So as I said, I think we need to change the way we are doing it. We've always been careful to show results without weights and not selecting models or anything like that. And when I started to have this, I mean, not problem, but this question happen when I was working on the 2300 extensions, because some groups submitted 10 or 11 subsets doing this exactly what you're mentioning with parameter uncertainty. And I couldn't really figure out a clever way in a short amount of time. And so I just had results shown selecting one condition from each ice flow model, letting them decide which one was the kind of main contribution, and then also reporting results for the entire ensemble, because we don't want to ignore these results. But this is far from being an ideal way. So maybe emulators can help us with that, to both capture the parametric uncertainty and the ice models, and we will have to be careful about what instructions we gave them, because they're just going to respond to our instructions. So how do we compare them? Starting to talk also about, there also people have looked at like how to combine models with different levels of like physics, and like how do we put them together? I'm starting to think about it. I don't have really good answers for now, but I think maybe that's another example where we have to look at what's been done in other disciplines. Climate models have been around for much longer. Other or even completely different scientific disciplines. So I don't have a good answer for that beyond, we need to look at it. We need to start to talk to people who know what they're doing, because otherwise I'm afraid we won't really take advantage of all these new capabilities and all these results that we're going to have. If you have ideas, happy to hear them.
No, I think it's good to discuss that in the future. I just wanted to throw in just one little thing, and that was, you mentioned that all these grounding lines for the different models that showed the unstable retreat in the Thwaites Basin, it was all according to the same slope. Well, I checked this slope, and the slope is around, 200 kilometers in 50 years, which corresponds to 10 meters a day, if my calculations are good, which is a bit the upper limit that is used of retreat rates in the cliff collapse parameterization. So it's quite similar to in magnitude at the upper end of the magnitude, this retreat rate.
Yeah, no, that's great. Thanks for adding that. Maybe it's overestimated. Who knows? It's under relatively warm conditions that happen mostly in the 22nd, 23rd century. So maybe the conditions are really warm there, but that's kind of feeding back on this other process. So thanks for the.
But
yeah,
it's interesting to see that all these models show, similar retreat rates without being parameterized.
No, and it's really the grounding line response, and it's mostly controlled by the geometry. There's also uncertainty in there, but we all use the same geometry. So another thing to think about, if we had different geometries, probably the response would be different. Another thing to throw on the table of things we need to improve. The list is really long already. We can add more.
But thanks a lot. Great talk.
Okay, do you have any other questions? Okay, well, I guess we can leave it there. So, thanks again, Helen.
Sure. Thank you all for joining. And now you can go back to your other reality. Thanks, everyone.